The error rate didn't spike. It exploded. Slack went from quiet to unreadable in seconds. Checkout failing. User stuck on payment page. Seeing 502s across the board. Pager duty escalated to critical. I opened Grafana. Request rate was at a level I had never seen before. Then I looked at latency. Flat at first. Then a sudden vertical climb. And then the real signal. Success rate dropping below 60%. Black Friday had just started, and checkout was breaking. We were running on AWS, primary region in US East 1, EKS cluster handling the application layer, CloudFront in front, then an application load balancer routing into Kubernetes. We had about 90 microservices. Traffic during normal peaks was around 3K requests per second. For Black Friday, we had prepared for 10K. Autoscaling was configured. Horizontal pod autoscaler based on CPU and request rate. Cluster autoscaler for node scaling. Database layer was RDS PostgreSQL with read replicas. Redis for caching and session storage. CI/CD was GitHub Actions with Argo CD managing deployments. Monitoring stack included Prometheus and Grafana. We had load tested. We had scaled up ahead of time. Everything looked ready until real traffic hit. Users could browse. Product pages loaded. Search worked, but checkout failed. Add to cart worked, but payment hung, then timed out. From the outside, it looked like a payment issue, but payment provider metrics were normal. Inside the system, services were healthy. Pods were running, no restarts. CPU usage was high, but not maxed out. Database CPU was elevated, but within limits. Yet checkout requests were failing, and only checkout. That narrowed it down. First thought was payment gateway latency. We checked external calls. Response times were normal, no errors, so not external. Next thought was database bottleneck. Checkout involved multiple writes, orders, inventory payments. We checked query performance. Slow queries had increased, but not enough to explain the failure rate. Then we looked at connection counts. That's where things changed. Database connections were maxing out, spiking and staying high. Even read replicas were under pressure. Now we had a lead. Too many connections. But from where? We traced requests through services. Checkout service called inventory. Inventory called database. Everything converged at the database. But that was expected. We had sized for this. Then we looked deeper. Connection pool metrics. Each service had its own pool, and each pod maintained its own set of connections. As pods scaled up, connection counts multiplied. Now auto-scaling was kicking in. More pods, more connections, more pressure on the database. A feedback loop. Slack was escalating. We had minutes, not hours. The root issue was not traffic alone. It was how we handled connections under scale. Each service used a default connection pool size, reasonable under normal conditions. But under autoscaling, it became a problem. Each new pod opened its own pool. No global limit. So instead of handling more traffic efficiently, we flooded the database with connections. Connection limits were reached. New requests could not acquire a connection. They waited, then timed out. Checkout, being write-heavy and dependent on multiple services, was hit hardest. Other parts survived longer. We had scaled compute, but not controlled how it interacted with the database. First step was to stop the feedback loop. We reduced the max connection pool size per service. That immediately lowered pressure. Then we scaled down certain services. Counterintuitive, but necessary. Next, we introduced PG Bouncer. That allowed many application requests to share fewer connections. Connection pressure dropped. Checkout success rate started climbing. We added rate limiting to give the system room to recover. Within about 40 minutes, checkout stabilized. Error rates dropped below 5%. Traffic was still high, but the system was handling it. What failed was not scaling. It was coordination. We assumed that scaling pods would naturally handle more traffic, but each pod brought its own demand. Detection was also incomplete. We monitored CPU and latency, but not total connection footprint. Database connections are finite. In the end, the system did not fail because it could not handle traffic. It failed because it handled it the wrong way.